All right. Hi, everyone. This is, can everybody hear and see us online as well? Probably, right? Okay, so welcome. This is Yu-feng. He's a research assistant at OpenGeoHub. My name is Johannes Heisig. I'm a PhD student at the Institute for Geoinformatics, University of Münster. And we gonna go away from raster for a minute at least today, because I think we're probably the only ones this week that wanted to explore a little bit about vector data. So we want to see how we can access large vector data sets in the cloud, and the tools we use we're going to present in a sec. So here's a very brief outline. I'm going to give an introduction on the data we use as an example data set here, and Yu-feng is going to pick it up to look at the tools and how we set up the cloud, did some considerations, how we can store and serve the data set, and then we'll jump into a couple examples. So we decided to use JEDI data. JEDI is a full waveform LiDAR sensor. It's a pretty exciting sensor, pretty exciting data set that it produces. So the JEDI mission has a goal of mapping carbon stock and carbon dynamics globally, and that focuses on vegetation mainly. So how do you measure carbon stock and so on? We can use a LiDAR sensor, so that's light detection and ranging for those of you who've never heard of it. By the way, who's worked with either LiDAR or JEDI data so far? Okay, cool. That's like half. Perfect. So this LiDAR sensor is an active sensor that sends us a signal and gets back this signal, and because the signal has changed, we can infer stuff from that. So it measures vegetation structure, including height and density, and we can look at this lower left graph here, which shows this in a little more detail. So this is a waveform that depicts the energy density of the returned signal according to the vertical height. And you see at the bottom in red, there's a ground return. And then we have between like meters 2 to 15 roughly, we have mainly the stem of trees of the canopy below the canopy. And in the upper 10 meters roughly, we see the canopy. The most energy is returned in this canopy. So we have the largest part of the biomass there. How does the data look like that comes from JEDI? So we have points, basically, point geometries that are attached to a number of measurements or derived metrics from the measurements. In our case, the data set has about 5.5 billion points attached to 95 variables each. So we're talking about a considerable amount of data. I think last time we checked, it was just under a terabyte. On the right lower image, you see an example sampling pattern of JEDI. So it follows the track of the ISS, and thereby it crisscrosses the Earth between 52 degrees north and south. So yeah, this is another example of how this orbit looks like. So JEDI is organized by, or the data is organized by NASA. It's distributed by NASA as well, and it's organized in many different orbit files. So one orbit file contains one of these green lines here in terms of data, and it's distributed in HDF5 format, and I would call that the opposite of cloud native and cloud optimized. And it's very difficult to extract exactly the piece of information you want, so the spatial domain at the time or whatever. So what we actually want as researchers is something that's easy to query in space and time, or possibly in other domains as well. And we want, of course, only the observations that matter, that have a certain degree of quality. With that, I pass on to Yu-feng to give you an information on Parquet and Arrow.
Yeah. So when we start looking at the JEDI data, the first thing we are thinking about, there are a bunch of H5 file online, but when we try to query a single area that we're interested in, we have to download all the file. And this H5 file, it's not really, you have to run the code from the NASA script and get through all the structure, including like a GeoPandas or something. So we're thinking about how can we make it more production and make it more accessible for other users. So we start looking at other geospatial factor format, which is table data format that can be used in this case. And then we found a Parquet data format which start as a lot of different layers, from data set to partition to file to row, group, column, chunk, and page. I will explain briefly here. So basically, the data set is the master directory that contains multiple Parquet files. This is single Parquet files and multiple Parquet files, and has metadata to connect each of the subfolder. And the partition is the subdirectories, where each partition reminds a column with the same value, so they can be easily organized by this partition level to the files. And now we can go into the detail of this individual Parquet file. So the Parquet file is like other factor data format like CSV or GeoPackage or FlatGeoBot, if you know this other cloud native format. It's organized in different columns. They have the different columns information and then geometry attached. And this special of the Parquet file is actually they have a footer metadata that attached. When every time you read the single Parquet data, you will first read the metadata and use the internal data structure to query the only necessary data that you will use for your analysis. So let's go back to the file. So how they organize that useful information inside the file. We have row group. Row group is a bunch of contiguous stored data that in a single Parquet file. And each row group have a column chunk. The column chunks have the individual columns we store in the horizontal way is the column chunk, then the vertical way is a row group. So you have all of the information of one column in each row. And in this case, you can use the footer metadata to filter out the row group by the optional statistic that calculate inside the row group and inside the column, trying to filter out which column you need for retrieval and which column you need for retrieval before you read all of the data. So in that case, we can store the data and without retrieving everything in a single Parquet file. And next thing I want to talk about is more high level. When we organize the data, is actually the partition things that I mentioned it before. So partition is like you have the same rope inside the file, and then you can use that to reconstruct the whole data set according to our definition. We can define the single time or single spatial intents that the points inside that extent will be loaded into a same partition with cutting up the file. And this is the one of the case, like 3 files. They are you can imagine that is a 3 file in 3 different orbits. And if you have the same time, for example, this partition can be in the time, and the red one is like they are within the same time range. They will put into one partition, and the green one is the different time range. They will put in another partition, and in that way you can partition your data set based on the geospatial definition. So this is one of the example that how this run actually, the algorithm, how this run actually to repartition the whole data. So if you can see that this orbit keep running, they are stored in the orbit structure so far from the first day that Jedi acquired the data to the last day. And if we use the spatial intent to partition the file, you can know that the first partition they contain the orbit 1 and orbit 2, and the second partition it's a little bit hard to explain, but I will try. And can I point it? No. Yeah. So no, I can't. So basically, when we process the Parquet file sequentially, and the Parquet point data inside the file with the same special intents will be put in the same partition. And by doing that, we can reconstruct the whole Parquet file organized by the orbit into the into the special into spatial and temporal blocks. We call it spatial and temporal blocks, and put into each partition. Each partition represent one block that have the same range of the time and the same range inside a bounding box, for example. And we think and now we know how to partition the file by transforming from the orbit to this geotemporal spatial temporal partition. And then we have to, like, we are very eager to find out what is the optimal partition that can be optimal to store into this structure. So it testing about the partition size to find the optimum partition size, and also what kind of partition structure can better represent the data. So, for example, we have here, we use a degree of the tile as a partition structure compared with 3 degree tiles and 6 degree tile, and lat long. So we first partition by the longitude, and then we partition by the latitude, and we test how long well this partition format can be extracted from our data set. And we see that if you have more detailed partition, that you will be extract faster than the last detailed partition. And if you do a multi-layer partition, first partition by latitude and then partition by longitude, it will be also faster than just partition by the 1 degree tile. And this is one of the experiments we do before we are trying to process the whole partition into our data set, and into our reconstructed data set. And then we also did a test to try to find the optimal partition size, because if you understand clearly, if you read the metadata have the information of the whole data set. But if you have so many partition and so many individual files, to read the whole metadata can be very time consuming. And if they take too long, it is not very usable for surfing this data. So in that case, we have to find the best partition that the metadata is visible to read in a certain amount of time, and we will not lose, because if you have,
we're balancing between the number of partitions, the number of individual files we store, and the size of each individual file. If we have very few, very large files, it takes a long time to open these. If we have a million very small files, then it's very hard to grab these headers from these tiny files. And so there's an optimum somewhere in the middle, and we try to find out where that is.
Yeah, so basically if you partition too much, you have too many small files, and you partition too less, you have too big file, and you load the big file from the cloud would take too long. And then we eventually found out the partition is around this natural log x equal to 8, around like 2,000 partition. And then that we design our partition structure that we are willing to reconstruct the file, and then we start building up the function to reconstruct the file. So we use this pyro dataset write dataset they have the function to write a dataset as a given format and partition. And I also wrote this article when I was trying to figure out what is the best way to do a parallelization to reconstruct the partition file, reconstruct the whole data set. Because the whole data sets were originally organized by orbit, but if you reconstruct by the spatial instance, you can just run it in parallel, each orbit by each orbit and each orbit. Because if you already have the defined range of time and space, you can give the orbit data structure to relocate inside the space-time structure, space-time block in parallel. Also, in that way, we can process the original JEDA file is 200 terabyte, but we stream all of the data into our data set using one server, 69 cores. We process 2 days and we finish everything. So this is how we reconstruct the file, and then we make this data set ready for other user to use. And after that, we also create, we also put it on the cloud. So basically, on the concept on the cloud, they are not covered too much. It's based on a concept of object storage. So each object on the cloud have a unique identity that can be found, that can be requests from the remote user. And what we proceed the file we have into the partition, each data set have each partition, each file have a unique identity that can be recognized by the cloud infrastructure. That user can use that information to query certain amount of data that they need inside the range they are querying. It's a little bit abstract, I will say, but this is one of the case that we have the Parquet file in our URL down there, and then we can use this polars package that was originally developed by a Dutch group, and they are building all of the lazy loading connecting to the cloud by Rust. And you have the API in R and API in Python at the same time. So we build all our S3 functionality based on that. So you can use the Polar to scan an individual Parquet file here. And then you can select the column that you are interested in. And you can filter out any information you want. So for example, here, we filter out longitude and altitude by giving a bounding box. So that is how, and after the filtering, they will not directly read into ourselves. They will store as an object, and when you collect the data, they will go loading directed the information inside what you are querying for to your local. So you can minimize the data that you will download from the cloud, and also optimize the speed to get the information in your area of interest.
You only load the metadata. You can construct filters, selections, all that, and it's still an external pointer as long as you don't collect the data. But only when you collect it, then it draws everything into memory or downloads if you like. So that's pretty handy. And with all the metadata loaded, like you can always check your query, like what columns, what filters have I applied currently before you actually hit the button. It's really handy.
You think someone say there's no sound? Okay. All right. So based on this structure, we have developed one of some functionality that can be used to they can be used to query the data that we process. So we already have this global lidar data one, and for the high quality data, and then we have the R notebook and the Python notebook that you can use to query the data that you want. And then we're also working on to process the ISAT2 data, which is another global LiDAR data. And I will show you a bit of this function and also show some function in R. We developed this in parallel. I'm doing in Python and Johannes doing in R. Yes. So this is the example that we can read we can query because the data is already reconstructed into geospatial perspective. So you can really just read the data really quick by sending the query. So basically here I define the polygon and the year that I wanted to retrieve and store into the object. And I can do the tile query to see what kind of tiles. So for example, this one is from the longitude 15 to 20 and latitude 5 to 10 and the year 2003, one of the object on the cloud. And you can also just read this URL. I think, for example, here, you can just have the URL and you can even just download the file. I mean, maybe not this one. Yeah, you can just download the file from the cloud, and the data we process, they are all free to use, and you can just download from a URL. We built this package for normal users that are not familiar with cloud system, but if you are really familiar with cloud system, you can just use our data set and you can just get every data that you want from the cloud. So we built this functionality or initially just try to help the people who don't have the knowledge on the cloud. But if you really skill at the cloud and you're a data scientist, you can just download based on the URL we have here in the individual partition and to get this data from the cloud by yourself. And Johannes, you have your, Johannes also developed his data access tool using R, and he have some example to show.
Yeah, I mean, basically the same functionality. The difference, I think, maybe like I used the opportunity to try to make some functions a little more user friendly, and we work with an interactive map, so you can draw your bounding blocks. You see in the background, hey, Jedi data this is the partition, by the way. These are 5 by 5 degree tiles. You can see how many points you roughly can expect there. And draw your bounding box according to that. Right, and as Yu-feng already mentioned, so you have two options of querying. You have this very rather sophisticated query that's like more directed to the basic user. So the basic user may want to have like a tiny forest or a tiny region where these exact points are interesting. Maybe he wants to filter right away before downloading. He doesn't have terabytes of space. He just wants exactly what he's interested in. So for him or her, that would be the bounding box query, where you actually use polars to do the querying on the cloud before you retrieve the data, right? Please notice that this takes a little longer, so it's not as efficient as just downloading a file without querying, obviously. And then there's the power user who may want to do like a country or a continent level analysis, and they may want all the Jedi data they can get. So they want to make sure that to get large areas, and they want to make sure that it's a download that is actually efficient, so they can make use of a tile query that then is executed in a parallel download, depending on what your machine can do, really. So yeah, of course, you can always take a look at what your area of interest looks like, and have a user interface, download that in parallel if you want. And what you get at the end is something like this. So this is a polars data frame. So this download took internet connection was better when we tested it before, but it takes a couple seconds usually to download a 5 by 5 tile with like hundreds of thousands or millions of points, and that's kind of okay. So here, this is 11 million points that are then retrieved to your disk. Right. Notice one thing that
Johannes.
Yep.
Have you tried comparing with PostGIS?
Say it again.
Comparing with PostGIS,
Right.
to compare how is it faster, slower,
No.
where is the difference? Because I mean the functionality is practically competing with PostGIS, right?
The data structure, the cloud native data structure is not the similar data structure. This one is more efficient than the storage and data transforming, and also for parallel reading. So I don't know. I check with the PostGIS the data size and the transforming time is slower than the Parquet. So this is why we try to adapt this system.
That would be nice to, have that as a benchmark to show different steps where the PostGIS is behind.
Yeah, that's a good point. Yeah, benchmarking would be nice.
Yeah.
Just as a last notice, so make sure to rescale your data. We stored this data on S3, and we tried, of course, to optimize storage capacity. So it's all translated into integers, all the numbers, and so we scale it. We applied a scaling factor. The information on that, like no data values, scaling factors, etc., they all come with the software with the functions we want to provide. But this is an important point. So yeah, I think if you have canopy cover values that are in the thousands, you may want to rescale that. Question?
So the data is stored in S3, right? So, but you query with bounding box. That means you transform the bounding box into something which internally the S3 can understand. That means you're transforming the query into something different. So,
yeah. So
is that internally you have some developed the system?
So the system is the way we do the queries is it's currently not really fancy. Let's say we have longitude, latitude values. We have longitude, latitude rounded to single integers to be able to make more efficient, quicker queries. Let's say for the 5x5 degree tiles, right? That's easier. And of course we can query the exact longitudes with floating point numbers. There is GeoParquet, which is also kind of doing that, but so far we haven't found like major differences because we query points and not polygons. It's we don't see a big advantage of using GeoParquet for now, but that'd be something for the future because it's still under development. I think the latest version is just a couple of weeks old, so we haven't looked into whether we can leverage GeoParquet versus the standard Parquet at the moment.
Yep. Just one point. Basically, it's a big complex. So we have the data set query level at the data set to find the partition that you want to retrieve. And another query on the individual Parquet file that will explain. You can read the metadata and filter out by the column. This is how we do bounding box query. First by the partition, then by the individual files. Yeah. And let me jump into some the last thing I wanted to share, which is basically we have one of the use case already to develop to use this kind of structure to organize the ISAP point actually and support the project we are doing with OpenGeoHub doing with the Lapiki to develop the shore vegetation map using the ISAT 2 point as the ground truth data to train the machine learning estimate the shore vegetation map. And then what we do to support the step is that we have this raw ISAT data, and then when we build this extra attributes by parallel computing when we process the raw file, and then we have this analyzed ready data set, and we give it to Lapiki, and they can try to build this lazy loading function to retrieve the point very fast to testing what kind of the attribute they want to use, what kind of the threshold they wanted to apply to get the best sample point within this Parquet structure. And then we process this 24.8 billion point to 4.9 billion point. The original is 20 terabyte, and then we have this high level of the ISAT point in 4 terabyte, and eventually we use 4.9 billion points for the testing of our modeling. And this is what we do using this structure to actually work in a real use case. And yeah, this is the end of our presentation. And I don't know, everyone tried to tell me Jedi or Jedi, and I don't know, something related to it, but I never watched Star Wars. And we are ready to take questions, please.
Please don't mix up Star Wars and Stargate.
Oh, I don't know what is this.
Very thin ice.
It's just a joke, yeah. Thanks a lot, yeah. So please go ahead with the questions.
We already had a couple questions so far, right? Yeah.
Yes, it's not clear to me if you were able, every time that you need to read the Jedi, you need to download in the full Jedi, or you were able to read streaming.
Sorry, say the beginning again, please.
If you need, in any case, to download the full
Jedi?
Yeah, HDF Jedi.
Do you mean,
or
you put it on the S3? Or you as a user?
No, you were transforming the Jedi to Parquet, no?
Yeah.
So this operation, you need to download the Jedi, or you can streaming through.
HDF5, as far as I know, is not capable of doing anything like that.
So you need to download in any case.
We download it, and because another reason is we also filtered and like remove bad quality stuff and repackaged that into partitions we found more practical.
Okay.
Not entire orbits, but just tiles.
Have you done some testing now for extracting information, the raster file through the lat long?
The raster file?
I mean, you will have lat long in this Jedi data.
Yeah.
Correct. And you need to retrieve information from a raster file in order to build up your predictor for the machine learning.
Extraction of points. When they're, I mean,
have you done some testing? In which tools are you going to use it? And
I mean, the objective here was to provide Jedi data, and you can do whatever you want with that. You can benchmark, but I mean, extracting points is nothing that we wanna like get into now. Raster data.
Okay.
Sorry. We actually did with the ISAT. So from this sample that Yu-feng showed, not the sample, the whole data set that Yu-feng showed in the end, we did a sampling design to generate about 50 million points spread all over the world, and we extracted for every point all the Landsat data for 1 year. So, but we also did per tile. So, for example, this operation took in our system, of course, running local, about 4 or 5 hours. So, but it's kind of ready to go to do to do this kind of extract. But it depends of what you use also.
Okay. Yeah. So if there are not any questions,
I have one question. So Giuseppe, could you please clarify what do you mean by streaming? Is it like without the hard copy on local drive, but directly into the memory? So reading them from S3 directly, because like if you want to compute something with it, you need it locally. Yeah. Yeah.
Yes. So, for example, I don't know if someone is aware about the vscurl function of GDAL. Okay, that you can reading something that is somewhere in the cloud.
Yeah.
Okay, so will be great due to that from the HDF. You don't need everything.
Right.
So it will be great to find the tools that can be even vscurl, because GDAL is reading HDF file. In this way, with vscurl or something similar, you can download only what you need. Right. Because in the Jedi it is very big, but then in the end you need the 6 algorithm plus the 95 quantile and so on.
Can you read from one single HDF file then, or can you read from multiple at the same time? Do you know? With vscurl,
you make a for loop and you read it one by one.
Yeah.
Yeah. So what we do having them test is like we provide the bounding box that they will go inside a single Parquet file and use that bounding bar information to retrieve the data only. So we only read the metadata in 2 seconds, and then we can query everything we want inside the bounding box you provide. And that is relatively fast in this we call this spatial temporal Parquet structure. Yeah.
If you have HDF5 files from JEDI, like thousands of them, you always have to loop through all of them and check, is my data in there? Oh no, it's not. Let me check the next one. And that, I bet that takes a while. This curl is not the fastest as far as I know. Like, I mean, it's convenient if you have one big raster and then you query parts, but if you have like thousands of files and they're organized like the ones I showed you with the orbits of JEDI, I could imagine that it's gonna be not so much fun.
So I wanted to say something.
Sorry. Okay. So there is a recent driver to read from Parquet and Arrow directly by GDAL. So it should be used in order to find if it is possible to access in a speedway, because it works on directly with the C and C++ library. If it is possible to use that in order to dive into the data set.
Yeah, so I just wanted, so I don't remember, maybe I missed it from the presentation, but the goal of this was that you are offering only the quality data from JEDI, if I'm, yeah. So you basically already pre-filtered data and pre-selected some attributes. So it's like it's a copy of original data, but filtered with the quality filters and everything. So I don't know if you mentioned this on slides.
Yeah.
But that's the goal of offering the service of JEDI data that are much more closer to be used for users. So I don't like term analysis ready, because for me is something analysis ready, for another person is another thing analysis ready. But this is much closer to the use of person than the original data set. That's the whole point. That's why there is this copy of the data, and that's why there is this styling structure. So it's cloud optimized, quality filtered data set compared to the original one.
Curated.
Yeah, thanks for Milutin. That is why we're doing this with Milutin to actually create this high quality data. So I take the question, Harn.
Did you now set up like an automatic pipeline to process the new data?
So that is this is kind of like we're having the discussion. So basically, what we have done here, the partition is expandable. So you have this stream of the orbit to this single partition, and this partition, the file inside the partition, they are actually a subset of the file, and they're still in time order, but they're only the subset where inside this partition. And if the new data comes in, they can still streaming into this partition. And then we will get the same. We'll get the same partition, but more data in when the new data set came. We only have to compile once to get individual Parquet file to increase the reading speed, but the time that we estimate it's about 4 hours just to when you stream out the file to get in this structure, it only needs like 4 hours to compile into the final data set we can put online to serve.
So the way we partitioned it is latitude, longitude in 5-degree increments and year. So very basic to get this optimal size of about 2,000 to 3,000 partitions. And that way makes it really easy to just add new data, of course, right? So for the year 2024, which we haven't had any data yet, it's easy to add that into the partition.
So kind of a related question. So I mean, currently JEDI, I think, is not on the station. There's some idea that it will go back on the station and continue collecting.
It's back.
Oh, it's back. Okay, as of last few weeks,
back.
right?
It has been back for a few weeks.
Okay. So with the ISAT data, at least usually every year there's a new version, and those versions have somewhat significant changes in terms of what columns, what information is made available.
Stuff, yeah.
So, I mean, at least like for the work that we're doing with ISAT, what we've had to do previously is say, okay, we're deciding we're going to use version X of this data.
Yeah.
How are you, I mean, are you guys planning on doing this for multiple versions, keeping old versions, getting rid of old versions?
I don't see that currently. So, I mean, it's rather, of course, rather user oriented. And if you're an expert and you do an analysis on different versions of some data set, I think you're capable of finding a way for that. I think we want to provide not analysis ready, as Milutin said, but something that's convenient, and that's the latest version of the data currently. We don't see a point in storing data that maybe then one person on the planet wants to use. So most people are interested in the status quo.
Well, no, just thinking about also like, you know, we've been talking about how do you make your work reproducible and how do you, you know, set up your entire workflow so that it's reproducible in some way.
Yeah.
And if you've published a paper that uses version X of the data, then
That is not.
Well, then
And
you
then
keep
the
that
old-
data and you store it in a container and you don't touch it anymore, right?
yes, the container of 40 terabytes. I mean,
Yeah.
like this is, you know, kind of where once we're at this type of volume of data, I think that's something as a community that we maybe need to think about.
I guess what you could do is to just not scrap the old ones, right? Like if that's at all feasible, like starting sort of at the moment that this is available for the public, like whenever people start using it, yeah, for the sake of reproducibility, you could just not scrap old versions and just put new ones on top. Obviously, nobody expects you to put like version 0.001.
This is certainly maybe in the long run an economic question for Tom and OpenGeoHub if he wants to have these terabytes on his online storage or not. We didn't commit yet to anything, but like Jedi is about 5 years old now. We have version 2 currently of the data, so it's been reprocessed once. There may be slight like improvements to the algorithms that create the data, but I don't see that there's a new version every year from now on. So I think it's a moderate problem, to be honest. And I mean, yeah, if it ends up to be 2 versions in the long run, that'd be fine. But I don't think it's necessary.
Oh, if you have the funding from NASA or ESA, then we will do it. That's all. Okay. We need to go.
Right.
My question,
Oh,
can
yes,
I?
please.
Sorry. So did you think about like using stack capability to like queries use data, or like, you know, you went directly onto GeoParquet probably, but
We considered Stack,
Yeah.
Because it's so widely used currently, right, for all sorts of raster data sets. We haven't seen a good working version for huge vector data sets, to be honest. So as far as I know, that you have to think about the question, what is a stack item, right, in a vector data set? If you have 5 billion points, is every single point an item? Not really. What is an item then? Of course, yeah, okay, you can use 5 by 5 degree tiles, but then again, you have millions of points. So where do you draw the line? So we haven't found a good answer to that, because like the overhead in metadata that Stack has for, like, let's say on the point level, and that would be just too much for that sort of.
we are kindly proposing a new stack spec
Okay.
because we are Oceanography Institute and we have a lot of like line vector data.
Mhm.
Like I don't know if you have heard about Argo observation. So we just flow instrument on the ocean, just let them flow for years and years. So we
Okay.
have vector data. So maybe we can talk afterwards.
Yeah, I'd like to chat.
Maybe our data is much smaller, but we have so many different data from different lines and so on. We just want to query at certain area at certain time, and there were some stuck things that we couldn't do, so we're kind of proposing. So
Yeah,
it could be
I'd like to hear about
Oh,
that.
yeah.
Thanks.
Thank you.
Yeah. Final words. I'm in the process of wrapping all these functions as an R package, and maybe I'm done by tonight or tomorrow, so I can share it on the Discord if anybody is interested in accessing Jedi in the near future. With that, thanks. Thanks, Martin.